Hello, and welcome to the Getting Started with the Stellaris EK LM4F 120XL Launchpad workshop. My name is Scott Bland, and I'm a senior instructor with the Technical Training Organization at Texas Instruments. I'm also the author of the material in this workshop. This workshop has been constructed to be extensively hands-on, and the overwhelming majority of your time will be spent working with the tools and writing code. If you don't already have some experience with embedded microcontrollers and using the C programming language, you need to acquire that experience before proceeding. There are many resources online that you can use to obtain that knowledge. In case you didn't know it already, this workshop is available at ti.com/Stellaris Launchpad Workshop as shown. That wiki site has links to all of the material you'll need to run this workshop. Let's get started. Chapter 1 is an introduction to TI's Stellaris LM4F series microcontroller and its peripherals and tools. In this chapter, you'll take a look at the Stellaris roadmap and the wider TI embedded processor portfolio. You'll also examine the architecture and features of the device and the design of the Launchpad board. TI has an extensive embedded processing portfolio, from the low end with our 16-bit ultra-low power microcontrollers like the MSP430, all the way up to multi-core DSPs like the C6000 and our ultra-low power DSPs like the C5000. In the middle, we have our 32-bit real-time microcontrollers like the C2000, the Delfino, Concerto, and Piccolo, which are very capable at motor control, digital power, lighting, renewable energy. I'll skip the Stellaris for a moment. Our Hercules devices are 32-bit ARM safety-directed microcontrollers containing M3s and Cortex R4Fs. Those are primarily used in safety, transportation, industrial, and medical, where two cores run in lockstep on the single piece of silicon. Next up is our 32-bit ARM microprocessors like the Citara A8 and A9 series. These are for high-end industrial automation, portable data terminals, places where you would be likely to see high-end operating systems. Then we get to our very, very high-performance devices like the C6000, the Integra, DaVinci, and our C6000 parts, up to 10 gigahertz multi-core devices with fixed and floating point and accelerators. These are for video, voice, telecom, medical, base station, lots of amazing things. You'll notice that in the middle of the chart here are all of our ARM microcontrollers. TI is one of the largest suppliers of ARM microcontrollers in the world. What we'll be dealing with today is the Stellaris ARM Cortex M4Fs. Cortex M4 is a specification by ARM. The F is a floating point unit that is added to the device. In the Cortex M4 specification, that's optional, but all of TI's M4 devices are M4Fs. All of them contain the floating point device. Our parts are currently up to 80 megahertz. Our flash goes to 512 kilobytes. We have peripherals like USB, Ethernet on many of these. It's the Ethernet MAC and PHY, CAN ports, ADCs, PWMs, SPI ports, and lots of other serial connectivity. These are being used in motion control, human interface, industrial automation, smart grid, robotics, an amazing number of places, $1 to $8. The Stellaris roadmap includes our legacy ARM Cortex M3 devices from the LM3S 800 all the way up to the LM3S 9000. These are all fixed point devices, from the general purpose devices with basically no major peripherals on them, to some that contain CAN, some that contain CAN and USB host device and on-the-go ports, and some may contain versions of that including Ethernet, MAC, and PHY on them. Currently in TMX, or being released for sampling right now, are our LM4F 11X, 12X, 21X, 13X, and 23X devices. The one that we're dealing with today is the LM4F 120H5QR. That will be released to production in February 2013. 80 megahertz devices, 256K of flash, 32K of SRAM, low power hibernate modes, two 1 megasample per second 12-bit ADCs, as many as 2 CAN ports on them, and some of the devices have motion control modules on them as well. The LM4F 13X and 23X also have USB ports that have host, device, and on-the-go, and include CAN ports on them. 80 megahertz, 256K flash, 32K of SRAM, low power hibernate, 2 1 megasample per second 12-bit ADCs, and motion control. In development right now are our LM4F 29X series that have USB and CAN on them, and they may also, the parts can also have Ethernet, USB and CAN, with speeds to 120 megahertz, flash sizes to 1 megabyte, 256K of SRAM, up to 2 CAN ports on there. They also include a nice wide 32-bit parallel bus interface and a cryptographic module on them as well. The Stellaris LM4F 120 series microcontrollers have a wide range of peripherals and capabilities. If we take a look at the diagram on the left-hand side, we can see the ARM Cortex M4F core, which sports JTAG access for testability, as well as serial wire debug for testability. We have the NVIC nested vectored interrupt controller. We have the memory protection unit. We have the floating point unit, and we have the embedded trace macrocell for extended testing on the device. For memory, we have 256K of flash, 32K of SRAM. We have an onboard ROM. I'll talk about the contents in a moment, and 2K of EEPROM. On the analog side, we have a LDO voltage regulator for regulating the CPU voltage on the device. A series of analog comparators. We have 2 12-bit ADCs, that's up to 24 channels through 12 shared inputs, 1 megasample A to D conversion, and a temperature sensor on board. On the left bottom side there, we have a series of serial interfaces. Depending on how you decide to use the I/O on the device, you can have as many as 8 UARTs, 4 SSI SPI ports, a USB device port, a CAN port, or as many as 6 I2C ports. For the system control, we have the normal, very flexible clock system, reset, and system control. We also have a SysTick timer on board. That timer is many times used as a real-time operating system heartbeat timer, although you can use it as a regular timer resource on the device. We have 12 general purpose timers capable of PWM and capture and compare. There are 6 each 32-bit or 2 16-bit. The other 6 are 64-bit or 2 32-bit. We also have 2 watchdog timers, each of them driven by a separate clock domain for safety. GPIOs, we have, I'll talk more about GPIOs in a moment. 32 channels of DMA, a precision oscillator on board, and a battery-backed hibernate module that offers real-time clock as well as battery-backed SRAM. So we offer best-in-class power consumption as low as 370 microamps per megahertz, 500 microseconds wake up from low power modes, and real-time clock currents as low as 1.7 microamps. It's a solid roadmap to higher speeds, larger memory, and ultra-low power. Stellaris LM4F devices have a 32-bit ARM Cortex M4 core inside them. The M4 core runs the Thumb2 instruction set. That instruction set is a combination of 16 and 32-bit code. Combining those offers or allows you to use 26% less memory and is 25% faster than pure 32-bit code. The system clock frequency on these devices is up to 80 megahertz. At 80 megahertz, we offer 100 dry stone MIPS. The device has very flexible clocking system on board, an internal precision oscillator, an external main oscillator that can drive a phase lock loop, an internal low frequency oscillator, and a real-time clock through the hibernation module. The instruction set and hardware offer saturated math for signal processing. We have atomic bit manipulation or read, modify, write capability using bit banding. We have a single cycle multiply and hardware divider on board. Data access here is unaligned for more efficient memory usage. We have both privileged and unprivileged modes. The privileged mode can limit, or excuse me, the unprivileged mode limits the access to the MPU registers, the systic, the nested vectored interrupt controller, and possibly some of the memory and peripherals, primarily to promote safety in terms of thread access, and sometimes RTOS's real-time operating systems require that. IEEE 754 compliant single precision floating point unit is on all TI M4F devices. We also have JTAG and serial wire debugger access to the Stellaris microcontrollers. The embedded trace macro is currently accessible through the Kyle and IAR emulators. The microcontroller on the Launchpad is an LM4F 120 H5QR. The memory inside that device has 256K of flash memory, single cycle to 40 MHz. Above 40 MHz, we have a prefetch buffer and speculative branching to improve the performance. There's 32K of single cycle SRAM with bit banding. We'll cover bit banding a little later. All LM4F devices have an internal ROM. Those ROMs are loaded with Stellarisware software. They have the Stellarisware peripheral driver library, which can save you a significant amount of space when you're writing your code. They have a Stellaris bootloader. They have the AES cryptography tables in them and CRC error detection functionality. We also have a 2K EEPROM that's wear leveled at 500,000 program array cycles, 10-year data retention, and there's a 4 clock cycle read time on this. In most designs, designers have to incorporate a EEPROM onto the board. In this case, you don't have to allow for that or pay for that. If you look at the memory map over on the right hand side, the flash memory starts at 0, the ROM memory starts at 1 million, the SRAM starts at 20 million. At 22 million is a bit banded mapping of the exact memory that's sitting at 20 million, the SRAM. The peripherals and EEPROM start at 40 million. We've bit banded those peripherals at 42 million. And there's instrumentation, the embedded trace macro, and some other stuff starting at E0 million. To continue the peripherals, we have a battery-backed hibernation module, which offers internal and external power control through an external voltage regulator. A separate real-time clock and power source. The VDD3 on mode can retain the GPIO states and its settings when we go into hibernation. We can wake on the real-time clock, or we can wake on a pin. There are 16 32-bit words of battery-backed memory for saving the processor state during hibernation. We have a 5 microamp hibernate current with GPIO retention, 1.7 microamps without. That's very, very low. Serial connectivity on these parts. We have a USB 2.0 device port, as many as 8 UARTs, depending on what you use the pins for, 4 I2C, 4 SSI SPI ports, and a CAN port. Looking at some more of the peripherals, there are 2 1 megasample per second 12-bit successive approximation A to D converters. The two parts share 12 shared inputs. Any of those inputs can be single-ended or differential. There's an internal temperature sensor, 4 programmable sample sequencers that we'll talk about later. Very flexible trigger control. You can trigger it with the processor through the software, with the timer, with an analog comparator, or directly from a GPIO pin. The voltage reference on this device, since it's cost reduced and we don't have as many pins to put an external reference, we're using the analog voltage and ground. There's optional hardware averaging. We have 2 analog comparators per device and 16 total digital comparators in the ADCs, and they're DMA enabled. On the GPIO side, depending on how you deal with the muxing of the pins, if you're using them for other purposes, you can have anywhere between none and 43 GPIO. Well, any GPIO can be configured edge or level triggered to interrupt. You can initiate an ADC sample or a DMA transfer directly from a GPIO pin. The toggle rate can be as high as the CPU clock speed on the advanced high performance bus ports. On a standard port, it's half the CPU clock speed. The inputs are 5-volt tolerant. You can have a programmable drive strength of 2, 4, or 8 milliamps. In the 8 milliamp setting, you also get slew rate control. And there's a programmable weak pull-up, pull-down, and open drain for every pin. Finishing out the peripherals, we have a memory protection unit that generates a memory management fault on incorrect access to regions that you've configured. We have a series of timers, 2 watchdog timers with separate clocks and user-enabled stalling. SysTick timer, it's a 24-bit high-speed timer that's generally used for RTOSes, but it's also available as a general-purpose timing resource. There are 6 32-bit and 6 64-bit general-purpose timers. All of those timers can be split in half, and they all have PWM and capture and compare modes. They can also be daisy-chained or combined together to generate longer periods. And all the timers listed there have user-enabled stalling. When you halt the processor in the debugger, you can halt these timers as well. The micro DMA is a 32-channel DMA that offers basic ping pong and scatter gather modes. They have 2 priority levels on the transfers, and they can be 8, 16, or 32 bits in size. The DMA can also generate interrupts when it finishes the transfer. We have a nested vectored interrupt controller on the device. We offer 7 system level exceptions and 65 interrupts with 8 programmable priority levels. So your vector table is not set in stone. You can go in and reprogram the priority levels if you choose. We also offer a very interesting feature called tail chaining that we'll describe later. It's deterministic. It's always 12 cycles for an interrupt, or 6 with tail chaining. And we have automatic system save and restore. The Stellaris Launchpad board has some impressive features for a small price. The onboard processor, there in the middle of the board, is a Texas Instruments Stellaris LM4F 120 H5QR microcontroller. It's a version of the ARM Cortex M4F family with 64 pins and has a top speed of 80 MHz. The Launchpad has 2 USB ports, one at the top for emulation and one on the left side as a device mode user port. The board can be powered through either port using the power switch in the upper left. There are 2 user push buttons at the bottom of the board. The one on the right is also connected to the wake pin on the microcontroller that will wake it from hibernation mode. A reset button is provided in the emulator area of the board in the upper right. Just below the reset button is a tri-color LED that combines the red, green, and blue LEDs into a single package. To the right of the device USB port are 2 test points where you can measure the current draw of the microcontroller. They are currently connected by a jumper. There are 2 crystals on the board, a 16 MHz one that drives the main oscillator and a 32,768 Hz one that drives the real-time clock oscillator. Since many computer USB ports can deviate significantly from 3.3 volts, an onboard voltage regulator is provided. Expandability is an important aspect of all TI's Launchpad boards. The Stellaris Launchpad features the Booster Pack XL pinout, which offers additional signals while still supporting existing booster packs. All Stellaris devices offer support for multiple integrated development environments, or IDEs, Mentor Graphics, Mentor Embedded, Sorcery Code Bench, IAR Systems Embedded Workbench, ARM Keil Microvision IDE, and Texas Instruments Code Composer Studio are all supported. Code Composer Studio, or CCS, will be our tool of choice in this video. In Lab 1, you'll obtain and install all the needed hardware and software, as well as test out the pre-installed application software on the Launchpad board. Since the installation steps are well documented and pretty straightforward, Let's skip them and start with examining the kit contents in Step 25 of Lab 1. The Stellaris Launchpad kit contains the following items: a README first car, the LM4F 120H5QR Launchpad board, and a USB A male to micro B male cable. Connecting the board to your laptop is very simple. Just connect the emulator port marked Debug to a free USB port on your laptop. The driver installation is covered in steps 26, 27, and 28. Don't forget to write down the port number that Windows assigns to your Stellaris Virtual COM port when you get to that step. Do the applicable steps and we'll pick up the video at step 29. Your Launchpad board came pre-programmed with a quick start application. Once you've powered the board, this application runs automatically. You probably already noticed it running as you install the drivers. In step 29, make sure that the power switch in the upper left-hand corner of your board is in the right-hand debug position shown. In step 30, the software on the LM4F 120H5QR uses the timers as pulse width modulators, PWMs, to vary the intensity of all three colors on the RGB LED, red, green, and blue, individually. By doing so, your eye will perceive many different colors created by combining those primary colors. The two push buttons at the bottom of the board are marked SW1 and SW2. I'll press and hold switch SW1 here to move toward the red end of the color spectrum. Press and hold SW2 to move toward the violet end of the color spectrum. If no button is pressed for 5 seconds, the software returns automatically to changing the color display. In step 31, press and hold both SW1 and SW2 for 3 seconds to enter hibernate mode. In this mode, the last color will blink on the LEDs for a half a second every 3 seconds. Between the blinks, the device is in the VDD3 on hibernate mode with the real-time clock running. Pressing SW2 at any time will wake the device and return to automatically changing the color display. In step 32, we can communicate with the board through the UART. The UART is connected as a virtual serial port through the emulator USB connection. You will need the COM port number that you wrote down in either step 23 or step 24. In the following steps, I'm going to show you how to use the connection to the board using PuTTY on this board. If you're using Windows XP, you could also use HyperTerminal. Double-click on PuTTY.exe on your desktop. Make the settings shown in step 34 and then click Open. Your COM port number will be the one that you noted earlier. So here we're going to use COM34, a speed of 115,200, and the settings are 8, 1, none, and none. So when your terminal window opens, press Enter once, and the Launchpad board will respond with a caret indicating that the communication is open. In step 35, you can communicate to the board by typing the following commands and pressing Enter. Go ahead and type help. If you type help, the board will generate a list of commands and information and things that it can do. Among them are intensity. So we'll try intensity 1 here. This will adjust the LED brightness between 0 and 100%. So we should be able to notice on the board that the LED is very dim. So go ahead and send intensity 100 to the board, and you'll notice now it's very bright. In step 36, go ahead and close your terminal program.